Like immortality or perpetual motion, time travel is one of the enduring fantasies of the human race. But until recently, the view held by scientists has been that time travel is impossible, not because there is any law of physics forbidding it, but because if it were possible, it would create all sorts of paradoxes. I study time travel as part of my work as a theoretical physicist. I'm interested in anything that is fundamental about the way the universe works. I want to know the way things are and how they behave at the deepest level possible. The Newtonian picture of the universe, with its mechanical view of time, has been replaced by modern ideas of relativity and quantum mechanics. Prior to these, time travel had seemed impossible. However, research being carried out by physicists, myself included, has now shown that most of the objections to time travel are not really obstacles at all. We may not be able to build a time machine tomorrow, but at least it now seems that building one would not be impossible. In scientific circles, time travel has become respectable. As a theoretical physicist, I spend a lot of time just thinking. I deal in ideas. My laboratory is my home here in Oxford. My equipment is a personal computer, a pencil, and a piece of paper. I keep in touch with other scientists around the world via electronic mail on my computer. One of them is Frank Tipler of Tulane University in New Orleans. He has been studying time travel since the early 1970s.
The simplest example of time travel is what I'm doing now, sitting in this armchair. I am now moving into the future. A more interesting example, however, of time travel was that conducted by two atomic clocks, one stationary in Washington, D.C., and the other one traveling in an airplane to Europe and back. The clock, which traveled on the airplane, which accelerated, actually went through less time than the clock which was stationary. So the clock that moved into the future of the clock that stayed home.
Einstein's special theory of relativity predicts exactly what happens to moving clocks. If somehow the aeroplane had been moving faster than the speed of light, then it could have traveled into the past. Unfortunately, the same theory also predicts that it takes an infinite amount of energy even to reach the speed of light. Therefore, simply increasing your speed is useless for time travel into the past. Atomic clocks and armchairs are not what we normally think of when we speak of time travel. What usually springs to mind is traveling far forwards into the future or back into the past. To see how this might be possible, we need to look at the physicist's picture of time. As H.G. Wells wrote in his book The Time Machine over 100 years ago, "You must follow me carefully. I shall have to controvert one or two ideas that are almost universally accepted." There are really 4 dimensions, 3 of which we call the 3 planes of space, and a 4th, time. Our present view of time is captured in the 2 great theories of modern physics, quantum theory and Einstein's general relativity. Chris Isham is trying to link the 2 together.
In Einstein's picture of the universe, space and time are considered together as a single sort of block. One of the most striking features of this block universe picture of space and time is that there is a certain sense in which the past and the present and the future all, as it were, exist at once. They have the same sort of status. And of course, if you're interested in something like time travel, and I suppose there's a certain sense in which you want that to be true, because if you're going to go back into the past has to, in some sense, really be there to be real.
From the point of view of modern physics, space and time are not independent entities, but they are linked together in an indissoluble whole called space-time. That means that it's not just the present that exists. The future also exists. The past also exists. The future and the past are as real as the present. From the point of view of physics, the dinosaurs exist, even though there's been no dinosaur on Earth for 70 million years.
Now listen to me. When people think of the past, they think of it as dead, as something that happened long ago. Greece, Rome, Carthage, Egypt. But when does it really begin? Well, isn't it obvious? It begins an instant ago. The dead past is just another name for the living present.
To many, Einstein's view of space-time is a difficult concept to grasp. The idea that our destinies might be mapped out in advance takes some getting used to. Each instant in this horse's existence represents an event in space-time and indicates where in the universe the horse was at that moment. The horse traces out a line in space-time. But because time isn't a separate entity, space-time has a very unusual feature. In the space-time view of the world, nothing moves. There is no particular moment called the present. Space-time shows the entire history, past, present, and future. In space-time, you can look at all times at the same time.
Our perception of time is due to our consciousness moving up into the future. The future, however, is already there.
The space-time view links the past, present, and future, but it doesn't necessarily dictate the order that they come in. As a time traveler, you would see things happening in a very disconcerting way. You could also expect to meet a younger or even an older copy of yourself. Time travel is not about changing the direction of time, but about getting space-time itself to take you back into the past. If this is space-time, and B is later than A, then the only way of getting back to A is if there's a loop in space-time. You're late. I knew you would be.
Sir, I have a time quake approaching.
Paradox, time quake approaching. 4, 3.
A paradox, Louise. You've changed the past. I know damn well we can't change the past. It catches up with us.
A common argument against the possibility of time travel is called the grandfather paradox. The idea is this. The time traveler gets in his time machine, he goes back into time, he shoots to death his grandfather before his grandfather has a chance to father his father. Therefore, the time traveler cannot exist because his father never existed. Therefore, since the time traveler doesn't exist, he can't go back into time and shoot his grandfather. We obviously have a logical contradiction. Many people have thought in the past this has ruled out the possibility of time travel.
If it is possible to build a time machine, surely people in the future would have used it to travel into the past. But since no one has seen any tourists from the future, some take this as further evidence that time travel is impossible. Although the grandfather paradox would seem to rule out time travel, this is not the end of the story. So far, we have confined ourselves to Einstein's view of space-time. To see why time travel is possible, we have to take into account the strange implications of quantum theory. At present, our best theory of matter and energy, and indeed reality, is quantum theory. At the most straightforward level, this allows us to predict how things like electrons, atoms, and light interact with each other. For instance, the transistors in your television set were designed using quantum theory.
Quantum physics really is an extremely successful theory at describing the whole of atomic physics and subatomic physics. And all sorts of things in daily life actually depend on quantum mechanics, the whole communications industry, television sets, radio sets, digital wristwatch, nuclear power for that matter. All these things are very much quantum mechanical. And parts of the theory have been tested to a phenomenal degree of accuracy, 1 part in a billion, that sort of size. But also it must be said it has some very peculiar features about the picture of reality which it portrays.
In my most recent work, I have been looking at how quantum theory could be applied to a hypothetical computer which calculated according to the principles of quantum mechanics. I did a calculation assuming that time travel was possible. As part of that calculation, I took information from the output of the quantum computer and fed it to the input before it had even left the output. Now, if time travel into the past was impossible, the result of my calculation should have been a contradiction. I'd expected a paradox, but surprisingly, I didn't find one. Time and again, my results showed that nothing bad happens if information goes back into the past. It all works perfectly. And if information can do it, there's no theoretical reason why human beings couldn't time travel as well. It was quantum theory that allowed the message in my quantum computer to go back in time. The explanation for why this is possible relies on one of the most bizarre ideas of quantum theory, the many worlds interpretation.
Well, the many worlds interpretation of quantum mechanics is very peculiar in the following respect. That first of all, one has to say that all of quantum mechanics deals with probabilities of things happening, just like tossing a coin. He says it's the fundamental property of nature. Now, when you actually toss a coin, of course, usually you toss it, it comes down heads or tails. Now, the many worlds interpretation of quantum mechanics is that when you come to the analogous operation in quantum theory, there is a real sense in which both possibilities actually occur. So rather than doing either this or that, you get both. And these are thought of sometimes as being, therefore, different worlds. It is as if you like, the universe has branched or split at that point into the two copies of itself, one where it's come up heads, one where it's come up tails.
Taken literally, the equations of quantum mechanics say that each time the pinball hits a bumper, it bounces off in all possible directions. Consequently, the ball follows many different lines in space-time, all of which actually happen. But if all these life histories are actually happening, the obvious questions are, where are they, and why do we see only one? Well, according to the many worlds interpretation, all the life histories do actually happen, but each occurs in its own separate, parallel universe. We only ever see one universe because there is almost no communication between the parallel universes. They each proceed on their independent ways, along with their copies of you, me, the pinball, and the world. What holds for the pinball machine holds for the universe as a whole. Reality, then, does not consist of one universe, but of a multiverse, comprising a large number of broadly similar, parallel universes.
The many worlds interpretation of quantum physics is one of these things that generates intense emotion amongst theoretical physicists. Some are very much in favour, some very much against. But there is one domain of physics where it's almost, I think, obligatory, and that's quantum cosmology.
Quantum cosmologists use quantum theory to study the way space and time behave from the creation of the universe onwards. They rely on the many worlds interpretation in their calculations.
The many worlds interpretation of quantum mechanics sounds completely bizarre. Even to most physicists, it seems absolutely crazy that there could be other copies of ourselves out there with which we could never interact and never see. However, there is one field of physics in which the majority of practitioners believe in the many worlds interpretation. That's quantum cosmology. A poll was conducted amongst the leading quantum cosmologists in the world, and an overwhelming majority of these people said that they believed in the many worlds interpretation of quantum mechanics. The field equations of quantum cosmology force us to believe in the many worlds interpretation.
Not quite clear, is it? I can see by your face that you're not certain. You don't understand.
It's part of the normal process of science to be deeply skeptical of radical new theories. But it's wrong for scientists not to take a theory seriously just because it seems outrageous. 360 years ago, the Inquisition threatened Galileo with torture because he claimed that the Earth was rotating. To the Inquisition, it was obvious from personal experience that the Earth doesn't move. But here at the Science Museum, the slow turning of this Foucault pendulum shows that Galileo was right. In everyday situations, it doesn't matter whether the existence of parallel universes is taken seriously, just as it doesn't matter whether the rotation of the Earth is taken seriously. But some concepts, like time travel, only make sense if the parallel universes really do exist. One person who is not convinced by these ideas is Stephen Hawking. He has recently proposed a new law of physics, which says that time travel is impossible. He calls it the chronology protection principle.
According to Einstein's general theory of relativity, space and time are warped and distorted by the matter and energy in the universe. It might therefore be possible that they could be warped so much that you could go on a journey and come back before you set out. This could cause all sorts of problems. Perhaps fortunately, it seems there may be a chronology protection principle which prevents travel into the past, and so means that we don't have to rewrite the history books. What seems to happen is that when space-time gets near to allowing travel into the past, a large number of particles appear, and these prevent one warping space-time anymore. The existence of a chronology protection principle is supported by theoretical work that I, and other people, have done.
Stephen Hawking has defended recently what he calls the chronology protection conjecture that says time travel is absolutely impossible. I think he's wrong. I think that looking carefully at the detailed arguments which people have produced indicates that it's quite plausible a time machine can be constructed.
The paradox of time travel arose because it was assumed you traveled back to the same universe. But what if we didn't go back to the same universe we started from? What if we went back to one of the parallel universes? In our original time machine model, the space-time loop took us back into the past in the same universe. But quantum theory says that there are many parallel universes. Our loop, instead of joining back onto the same universe, links up at an earlier time with one of these parallel universes. A traveler who enters the time machine in one universe will not only end up at an earlier time, but also in a different universe. One of the consequences of this movement is that you could meet up with the copies of yourself who live in the parallel universes.
Not bad. Dudes, you guys are gonna go back in time. Yeah! You are going to have the most excellent adventure through history. Who are you guys? We're you, dude! Whoa.
Suppose I do an experiment. With this time machine, I will travel through quantum space-time, back a few minutes into the past. To test the paradox, I will shoot my slightly younger self. Let's look at only two of the many parallel universes. In the left-hand universe, I decide to go into the time machine and travel back in time to the right-hand universe just before I set off. So long, partner. The paradox is avoided because when I traveled in time, I also traveled into another universe where I shot a copy of myself. So long, partner. In my original universe, no one shot me, and so I was free to travel, and no paradox arises.
Passports, please. Moving ahead to February 12, 1999.
But what about the other objection to time travel? How do we explain the fact that we have not been invaded by hordes of tourists from the future?
One of the properties of a time machine is that you can never visit a time which is earlier than the moment the time machine came into existence. For instance, if a time machine is created in the 21st century, then it will be impossible for visitors in the far future to visit us. They can visit the 21st century, but not us. In particular, creating a time machine will not make it possible for us to see the dinosaurs. However, if another advanced civilization created many hundreds of millions of years ago a time machine, it would be possible to visit the dinosaurs.
So if you want to meet your own distant ancestors, you'll either have to find a naturally occurring time machine somewhere in the universe, or borrow a time machine created in the past by an extraterrestrial civilization.
Before anyone claims that UFOs are visitors from the future, let me say that I think any such alien visitation would be much more obvious and probably much more unpleasant.
Let me get this straight. A thing that looks like a police box standing in a junkyard, it can move anywhere in time and space.
Doctor Who's TARDIS is perhaps the best-known visualization of a time machine, but there has been no shortage of imaginative ideas about what a practical time machine would look like.
According to general relativity, gravity is a manifestation of the warping of space and time. Matter tells space how to warp, how to curve. If you have very massive body, which is rotating, then the rotation and massiveness of the body can twist space and time so drastically that near the rapidly rotating body, the future direction actually points into the past from the point of view of us here on Earth. If such a body actually exists in space, that rapidly rotating body would be a time machine. Rotating black holes have, perhaps, in their interior, regions where time and space are twisted around in just the way I have described, that the future points into the past. However, this would be useless to create a time machine because you could never get outside of the black hole once you fall inside.
If skirting close to a black hole sounds a little uncomfortable, there is another possibility.
One of the key ingredients in time travel is a tear being set up in space-time. Now, you can't do this in ordinary classical general relativity. You can have smooth bends in space and time, but you can't rip it apart. In the quantum theory, you find that these bends and warps can fluctuate, and they can become contorted in such a way that you can actually punch through and change what's technically called the topology of space. And so, for example, you go from a smooth surface to something like the surface of a donut, so it twists in on itself. Now, the interesting question is how big can you make that loop? The original studies tried to say it could be a large-scale loop, so you really could go back and see your grandfather. But the more recent idea is that really these effects could take place at these very, very tiny distances, which you get in quantum gravity.
At the moment, all routes to time travel are far beyond our technological capabilities. But more physicists than ever are doing research in this area. And all the traditional objections to time travel have turned out to be invalid. My gut feeling is that if technological obstacles are the only ones in our way, then one day time machines will be built.
It will be a pity if it turns out that time travel is not possible. It would have been exciting to explore the universe in time, as well as space.
Well, the subject of time travel is certainly very, very speculative, as indeed is the whole issue of how you combine quantum theory and general relativity. But in these sorts of topics, however far they may appear to be from ordinary daily common sense, you really are trying to address the fundamental ingredients of reality at the really sort of basic physical level. And in that sense, I think it is a very important program and well worth pursuing, even though it is, as I say, very speculative.
My personal belief is that we know nothing to definitely rule out the possibility of time travel. We've been doing intensive research on this subject for many years, and we studied carefully the laws of physics. We see no reason for thinking that time travel is forbidden.
Almost all of the discussion about time travel is beyond the present realm of experimental testing. But I have faith in the theory, and time travel is allowed by the theory. Maybe I'm an optimist, but there's an old saying in physics: whatever is not forbidden is compulsory.
Next week in Antenna, Professor Bob Williamson explores what has been described as the next revolution in medicine, gene